Okay, so now we're ready to look at the common emitter amplifier design simulations using LT-Spice. For the Prelab, you've calculated all the resistance values that you needed and rounded to the nearest standard value. So now the last part of this is just to verify using Spice simulation software. So if you open LT-Spice, you can place down all your components. I've already done it. And if you're not sure how to add the BJT, you can just click on Component at the top, look for NPN, click OK, and right click on it, pick New Transistor, and you want the 2N3904, and that will set up the model correctly. I don't need it, so I'll just delete it. But once you have everything wired up like shown, we'll be able to run the simulation. I chose VCC as 15 volts here for my design, and I think I spec'd for a gain of 24 or 26 volts per volt. So these are the resistor values that I came up with. The voltage source is going to be 10 kilohertz, 100 millivolts amplitude, so that's 200 millivolts peak to peak with 0 volt offset. And they give you this information in the hardware part of the lab. So it says to use 100 millivolts signal at 10 kilohertz. The simulation command is transient for 300 microseconds, so that we can get 3 periods of the waveform with a maximum time step of 1 microsecond. So nothing else special here. Once you have that set up, you can run. And I've plotted the input signal here in green and the output in blue. The peak to peak of the input I've measured here, so it should be about 200 millivolts peak to peak, which is what it is. And the output is 2.3 volts high and minus 2.44 volts low. So if you take the difference of those two values, that will tell you the peak to peak output is about 4.74 volts peak to peak. So 4.74 divided by 0.2 gives you a gain of about 23.5 volts per volt. So for sign off, you want a picture of the schematic, and you want a picture of the output waveform just like this, where you've labeled your high and low points so that you could figure out the gain. So input signal should be 200 millivolts peak to peak. Output signal for me was about 2.74, and then you can calculate the gain using those two numbers. And the last part is there's a third picture here where you increase the input swing so that you get the output to clip. So we know my gain now is about 24, and with a 15 volt supply I should be able to swing the output 10 volts peak to peak. 10 volts divided by 24 is 10 volts divided by 24 is 416 millivolts peak to peak at the input. So let's change this guy to, instead of 0.1 amplitude, we'll do 0.2, let's do 0.22. So the peak to peak is 440 millivolts, something a little higher than what the calculator just gave me. So we can rerun the sim now. and try to verify that I hit 10 volts peak to peak. So I'm going to delete all these data points here. I'm not going to bother measuring the input this time, I'll just measure the output. Get the max and the min. To be complete, we'll get the input too. It's because you'll probably want it for your picture. Okay, so peak to peak is 440 millivolts, and output is pretty close to 10 volts peak to peak. It's a little low, which means our gain was a little less than I anticipated. So you could increase this a little further and show that you meet your swing spec. And once you have that, just grab another picture of your waveform here and put it in this box so that you have it for your lab report. And just record your output swing with large input, just to prove that it's greater than your design spec. And that's it. When you're done, just submit this file with all of your images and measurements, and don't forget to include your LT Spice files in your submission.